Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 35 Organic Chemistry 2. Today we will continue on carboxylic acid derivatives and we will cover their reactions. Reduction of carboxylic acid derivatives. Recall from previous lectures, reduction of carboxylic acid derivatives to alcohols. Lithium aluminum hydride reduces acid chlorides, anhydrides, and esters to primary alcohols. Acid chlorides are more reactive than the other. Either lithium aluminum hydride or sodium boron hydride converts acid chlorides to primary alcohols. So, if we take an ester with lithium aluminum hydride, we'll form the alkoxides from these two parts. With the reduction of the carbonyl, of course, to give alcohol mixture. Well, how the mechanism goes: first, hydride attack on the ester, addition, followed by elimination to form the alkoxide of this part, okay, salt, and aldehyde intermediates which we cannot isolate. So, second, hydride attack to reduce the aldehyde to alkoxide primary, okay, hydrolysis of these salts give mixture of alcohols. Propose a mechanism for the reduction of propanyl chloride by lithium aluminum hydride. Propanyl chloride with lithium aluminum hydride attack as a nucleophile first, forming tetrahedral intermediate, elimination of chloride add, forming double bond aldehyde intermediate, reduction of the carbonyl with another molecule of hydride to give the alkoxide salt, okay. When we add acidified water, it turns to be alcohol, primary alcohol. Reduction to aldehyde. Acid chlorides are more reactive than other derivatives, and they are reduced to aldehyde by mild reducing agent. Using lithium tritertiary butoxy aluminum hydride, we can reduce the acid chloride to aldehyde. Also, we can reduce the ester using diisobutyl aluminium hydride to aldehyde, but at very low temperature. So, having the ester diisobutyl aluminum hydride in ether at -78 degrees Celsius, followed by addition of water, gives the aldehyde. So we can reduce acid derivative, acid chloride, using lithium tritertiary butoxy aluminum hydride, or we can reduce the ester derivative on acid using diisobutyl aluminum hydride at low temperature. Reduction to amine. We can reduce the amides and nitriles to amine using lithium aluminum hydride. So, if we have here primary two hydrogens, it will give primary amine, two hydrogen in here. If we start with secondary amide, like one of these will be R group, then would turn out to be secondary amine. If we have R group in here and R group in here, we call that tertiary amide. It will give tertiary amine. Okay, R here and R here and R here, that's tertiary amine. Addition of the hydride, then this lone pair will move on here to form the iminium salt, and this group will be out. Then the imine double bond will be reduced with hydride to form the amine. So we notice that using lithium aluminum hydride, then addition of water or acidified water, we turn the C double bond O of the amide into CH2. So this is a transformation. And if we have nitrile, we transfer C triple bond N to CH2 NH2. Okay? Give the expected products of lithium aluminum hydride reduction of the following compounds. Again, here we have an amide functionality, right? Well, with lithium aluminum hydride, we are going to reduce this C double bond O to CH2. Here we have nitrile. Well, with lithium aluminum hydride, we transfer this to CH2 and H2. Reaction of carboxylic acid derivatives with organometallic reagent. Grignard and organolithium reagent add twice to acid chloride and ester to give alkoxide. Protonation of alkoxide gives alcohol. So we have an ester, two equivalent Grignard or organolithium form the alkoxide, and upon hydrolysis it gives alcohol. Reaction of with acid chloride. Acid chloride with Grignard reagent gives ketones, because acid chloride are more reactive than ketones. So the first molecule reacts with molecule of acid chloride to form ketone. The second molecule of Grignard will attack on acid chloride because it's more reactive again than the ketone. So it will keep going, adding ingredient to acid chloride until the reaction is over. Grignard reagent can, in principle, give ketone without further reaction, but Grignard reagents are so reactive that this transformation is difficult to achieve in practice, and we always get a mixture. Okay, so it's not a clean reaction. So we have to find another way to perform this transformation to get ketone and stop the reaction. We use Gilman reagent, lithium dialkylcuprate, which we prepare from alkyl lithium with copper chloride to form this Gilman reagent, lithium dialkylcuprate. They are less reactive than Grignard and organolithium. They typically react readily with acid chloride, aldehydes, and epoxides very slowly to give ketones, and not at all with ester. So they react with acid chloride, aldehyde, and epoxide, not an ester. Okay? The reaction of lithium dialkylcuprate with acid chloride gives ketone and HCl yield. So we have here acid chloride with lithium dialkylcuprate cuprate, THF at minus 78, again very low temperature, to give ketone. Because ketones are much less reactive than acid chloride or lithium dialkylcuprate, they do not react further. Not like Grignard. There is a possibility in Grignard to react. Even the acid chloride is more reactive. Here, the reactivity difference between acid chloride and ketones with lithium dialkylcuprate, it's a little bit far away from each other. Okay. Reaction with nitrile. The Grignard or organolithium reagent attacks the electrophilic cyano group to form the salt of imine. Okay, so we have R prime to attack on here, addition reaction to form the salt. Hydrolysis of the salt gives imine. Hydrolysis of the imine in presence of drops of acid, it gives the ketone. So water at first protonation followed by addition minus H plus H to transfer this H to the NH2, then elimination of NH3 to form a ketone. Show how you would add a Grignard reagent to an ester or nitrile to synthesize 4-phenyl heptane 4-ol. This is a structure of 4-phenyl heptane 4-ol. Well, this carbon which carries OH will be our source of the ester. Okay, here, so we get this ester, and then this will be the Grignard. Okay, with 3 carbons. We use 2 equivalent, of course, from Grignard. Here, again, this carbon will be our ester source, and these 2 sides will be our Grignard. Okay, ester and then 2 equivalent. For this one, that's ketone, that's not alcohols. Okay, we can get this again cut in here. That will be from nitrile and Grignard. Okay, or we cut in here, that will be the nitrile and the Grignard. Complete the following equations. Now we have propanyl chloride. We add water. Okay, so we replace the Cl with an OH, acid, alcohol. We change Cl to OR, ester, RNH2, that will be Amide, right? Carboxylic acid, that will be anhydride, right? 2 equivalent of RMG Grignard followed by hydrolysis, that will be tertiary alcohol, right? Here is Gilman reagent, lithium dialkylcuprate, then you get ketone, right? If you reduce the acid chloride with sodium borohydride or lithium aluminum hydride, then hydrolyze, well, you get primary alcohol, right? you reduce this carbon to CH2. Right. With lithium aluminum with tri-tertiary butoxy aluminum hydride, that will give you aldehyde. Right? We are done with this scheme. What about this? Ester with water, acid, with alcohol, another type of alcohol we call trans-esterification in presence of catalytic amount of acid. Right. Amine, you get amide. Grignard, again, tertiary alcohol. Diisobutyl aluminum hydride, aldehyde. Lithium aluminum hydride, alcohol. We are done with this one. Now, missing reagent. How we can transfer this to that? What do we add in here? Okay, acetic anhydride. We need the source of CH3C double bond O plus, and we have here plus the center. Okay, all right. How we can transfer this to primary alcohol, lithium aluminum hydride? How we can make esterification on here? This is acid. Okay, Fischer, you add methanol in acidic medium, catalyst amount of acid. Right. Now, how we can get from amide to carboxylic acid? Hydrolysis, either acid hydrolysis or base hydrolysis. If you use base hydrolysis, you have to acidify the reaction mixture later on. How we can get from amide to amine, lithium aluminum hydride reduction. How we can get from amide to nitrile, elimination of water using phosphorus oxychloride or phosphorus pentoxide. What do we get if we react diacid with diamine? Heat. We know that acid with amine and heat, we get amide. So that will be, because we have two sides amine and two sides acid, that will be a polymer, polyhexamethylene adibamide. We call it nylon 66 because we have 6 carbon here, carbon and 4 carbons, 5 and 1 carbon 6, and we have 6 carbon in the amine. We call it nylon 66. Now we have this acid and diol, DiOH. Okay, alcohol and carboxylic acid will form ester. Right? Since we have two sides COH and two sides OH, we get a polymer, polyester, terylene. Thioesters. The thioester is formed from carboxylic acid and thio. Thioester are also called thiol esters and react the acid with thiol to give the thioester. Thioesters are more reactive toward nucleophilic acyl substitution, but less reactive than the acid chloride and anhydride. So thioester is much more faster than ester in nucleophilic acyl substitution, which means that SR prime is better leaving group. It will go faster. The enhanced reactivity of thioethers results from two major differences. First, the resonance stabilization of thioester is less than that of an ester. In the thioether, The resonance form involves overlap between 2p orbital on carbon and 3p orbital on sulfur. These orbitals are different sizes and are located at different distance from the nuclei. The overlap is weak and relatively ineffective, leaving the bond of the thioester weaker than the bond of an ester. Here is the resonance structure: lone pair from sulfur, delocalized here to give O minus, single bond carbon, double bond sulfur with positively charged. This resonance structure contribution is weak. The second difference is in the leaving group. An alkyl sulfide anion Sr prime with negative charge on the sulfur is a better leaving group than an alkoxide ion, because the sulfide is less basic than an alkoxide and the larger sulfur atom carries a negative charge spread over a large volume of space. Sulfur is also polarizable, more polarizable than oxygen, allowing more bonding as the alkyl sulfide anion is leaving. Well, in leaving system needs acylating reagents, but acid halide and anhydrides are too reactive for selective acylation. Also, they would hydrolyze under aqueous condition found in living organisms. But we need acylation or acylating agent in the naturally occurring system. Well, thioester is good. We can find as an example coenzyme A is a thiol whose thioesters serve as biochemical acyl transfer agent. Thioester in here, coenzyme A, nucleophiles attack via nucleophilic acyl substitution reaction, acyl transfer, and we get S minus coenzyme A. The total structure, chemical structure of acetyl coenzyme A, it's nucleotide part, dipeptide part, and at the end we find the thioester. Ester and amides of carbonic acid. Carbonic acid is unstable, dissociate to water and carbon dioxide, but carbonate ester is stable molecules. How we name this? Here we have ethyl methyl carbonate, and here is dipropyl carbonate. They are used as electrolyte solvents in lithium ion battery. Diamide of carbonic acid, urea, and a stable molecule at normal condition. This is amide. It's 1,2, 1,3 dimethyl urea. It's 1, 2, 3. So this is 1, 3 dimethyl urea, and here is 1, 2, 3. So it's 1, 3 dimethyl, 1, 3 dipropyl urea, and they are agrochemicals and pharmaceuticals agents. Carbonic acid, when we have one of the OH replaced by NH2, that's carbamate, or they call it urethanes. This is isopropyl methyl carbamates, And here we have methyl dimethyl carbamates. That's methyl for the ester, and here is dimethyl carbamate. Okay, here is one word, and here you have to leave space. Again, here is the ester part. So this is isopropyl, then space, then methyl carbamate. Okay? Carbamates are used as sprays or paints to kill insects, so they are insecticides. By affecting their brain and nervous systems, urethane are synthesized by treating alcohols or phenol with isocyanate. So isocyanate structure with alcohol, you get carbamates, urethane. Propose a mechanism for the reaction of methyl isocyanate with one naphthol to give sevine insecticide. Well, phenol has lone pair here for oxygen, will attack on this carbon, breaking this bond, or the carbon double bond O, form this species resonance structure. This is second resonance structure, minus H plus plus H plus. So move this H from this oxygen to that, and then tautomerism to give the amide bonding. Predict the product formed when phosgene reacts with bisphenol A. This is a bisphenol A, and this is phosgene. It has 2Cl bond, double bond, O, and then two OHs. What are we expecting? A replacement of this Cl with O, and again from the other side, one other two OH will replace the Cl to form polymer, and the polymer will be OCl, OCl, OCl. This unit, what we call it, repeating unit. Okay, and this is structure of polymer called lexan polycarbonate, very strong, clear polymer used in bulletproof windows and crash helmets. See you next lecture.